quantitative.
Primarily in quantitative. So what I would find interesting is what happens next time during your next practice test if you take the following list, and I'm going to type in the chat here. 3D geometry, uh, rate questions where I cannot choose my own value, um, probability questions, and combinations questions. I wonder what would happen if you looked at, if the moment you got any one of those, you immediately said, no, I'm out. I'm wondering how much time that would save for all the other problems.
Okay, interesting.
That's something that I work with a lot of people on, looking at problems and saying, I'm not going to start it.
Hmm.
So that's something that I would recommend there. Alex, you left a comment of 3D geometry without any other context behind it. Is that like a topic request?
No, you're saying if there's one area you'd skip over just to make sure, I'd say 3D geometry. That was
Yeah.
my answer for that question.
Yeah. Yep. 3D geometry tends to be a killer because it's all the length of geometry problems, and geometry problems can get very long, but literally to another exponential level of time consumption.
But also, I feel like I don't necessarily know the formulas well. So if you do want to cover it, I'm definitely happy with that. But that's one I'd skip over. And then also the fill in the blank ones in general, because
Hmm.
there's a chance to have an estimate with some of those other ones. Like if you got it right within range or something, you kind of could guess. There's a lot more of a meticulous effort into those fill in the blanks.
Okay. I will tell you that my current plan, based on an email request that I got, was actually to look at exponent questions, complicated exponent stuff. Um, my my lean would be to say we should do that before we do 3D geometry, because the exponents problems are something that you really want to have cold.
That's good.
Yep. Ashley, for yourself, any concerns that you have?
Wait, for me or I didn't.
Ashley,
Oh.
there's someone in the room named Ashley, and I was wondering if they could get on the microphone or type something in the chat. Margaret, the graph interpretation questions, I'm assuming you mean the data interpretation questions, that trio of questions that's all built on the same graph or same set of charts. That's always in the first section. Yeah. Main rule for those, if I need more than 3 data points to begin this problem, I'm not doing this problem. Count the number of data points you would need. If it's more than 3, move on to the next problem. I found that the thing that provides the most dramatic initial improvement for quantitative scores is getting the questions that you know you can get quickly correct first, and just banking a lot of time to come back and look at some problems later. I mean, imagine for a moment, and I would actually say in the second section particularly, if you get to the harder second section, when you do that, if you just burn 4 questions, and that will save you at least 8 minutes. Imagine what you could do with 8 minutes on the other questions in that section. And you'd still probably have time to go back and look at 2 of the ones that you burned. Joshua, any last calls for topic requests there? All right. Nothing coming in from Joshua or Ashley, which is okay. So let's go ahead. Let's dive in here. And I would like to begin by asking what may seem a silly question, but it is an honest question that I would like for people to answer. What is an exponent? You can get on the microphone or type in the chat, but that is the question to the group right now. a number multiplied by itself a certain number of times. Excellent. So I would actually like to begin just by putting 2 problems in front of the group. Oh, not quite what I meant to do. That's what I meant to do. Everyone take a few moments. Don't worry about solving them. That's not our goal right now. Take a moment. What are the similarities? What are the differences between these 2 problems? And again, type into the chat or go and get on the microphone to respond to that question. What are the similarities? What are the differences? So we have some negative exponents on 17, and we have some square roots in number 22. So that's a definite difference there. Joshua, is there any chance that you can get on the microphone? If not, just say, sorry, can't get on the mic in the chat. But I'm curious because I would really like to hear you expand on your statement. Seems that getting on the microphone is not going to be an option for Joshua. That's okay. Joshua, do you think that your comment is... Oh, thank you, Ashley. Okay. Fractional exponents while the left is only operating in integers. Okay. What's interesting here is that the idea of multiplying versus adding, or adding and subtracting, is for me actually the main difference between the 2. That for me is the difference between traditional versus non-traditional. An exponent is a command to multiply or divide, because negative exponents are just divisions. Because of this, we can split exponent presentations into 2 categories. Traditional, exponents, or roots, they work with the same rule set. Exponents or roots presented with only multiplication and division. Non-traditional, exponents or roots presented with addition or subtraction elements. We're going to leave that depiction of the themes there, and we're going to come back to this problem. And I'd like to everyone just take a few moments and give this problem a try. Everyone just take 2 minutes, give this a try. Let me know in the chat when you have, just say done when you have an answer choice that you would select. All right, that is about 2.5 minutes. Before we dive into this one, I want to just respond to Ashley's chat real quickly. Ashley, when you're down to just a few days before your test, focus on the things that you feel best at. Make sure that you are completely solid on those and make sure that you're very comfortable with how you can move through those very, very quickly. So that on Friday, when you go into the test, say, all right, this is either something I know or I don't know. If I don't know it, I'm going to just put a pin in it. I'll come back to it later. I will get everything that I feel best about first, get your guaranteed points, and then come back and try all of the other problems. Um, if you do that, you'll have more time at the end to try problems than you think you will, and you'll be very, very confident that you have made sure that you've answered all of the questions that you felt best at to the best of your ability. Excuse me, everyone. Is anyone else with Margaret on this? Feeling stumped? You can give me emojis in Zoom. You can give me something in the chat, or you can say, Josh, are you feeling a little stumped? All right. Yes, given the time allotted. Yeah. This problem actually has a lot of moving pieces to it. And the idea behind this problem more than anything else to me is looking at it and immediately saying, this is traditional exponents. I have exponents with nothing other than multiplication and division. And when I have traditional exponents, the beauty of it is I can go straight to the rules. And the rule for traditional exponents, I'll put this up here. Traditional exponents go straight to the rules. You can combine common bases or common exponents. If you do not have common elements, ask whether they are hiding, because they are there. We start by just copying the problem down. I have 10 to the negative 8. I'm putting them all in parentheses because adding the parentheses doesn't change the actual math, and it's going to make the next step, I hope, a little bit more clear. And so I look at this and I immediately want to think, all right, what is the largest element here? Open question to the room. What is the largest element in this problem? The 25. So Margaret, that 25 is no longer going to be a 25. I'm going to take that large element and I'm going to break it down into pieces. 25 can be written as a 5 times 5 or a 5 squared. Next largest element, the 20. Break that down into its pieces. A 20 is 4 times 5, but 4 is not prime, and my default will always want to be prime factors or something like this. So I'll rewrite that 4 as a 2 squared. Next largest element, the 10. The 10 is a 2 times 5. The 8 is a 2 to the third. And a 2, well, that's already prime. It's just a 2. Hold here for a moment. Does anyone have questions, comments, or concerns about the transformation so far? One of the major reasons why you want to be very clear about a differentiation between traditional and non-traditional exponents. Exponents and roots can be directly distributed across multiplication and division. They cannot be directly distributed across addition or subtraction. That is one of the main reasons why you want to make this division. to know where you can do direct distributions and where you cannot. On elements, if you ask where they're hiding, usually it will be in prime factor bases. So I can now apply each one of these exponents to the prime factor base. I can write this as 2 to the negative 8, 5 to the negative 8. What is 5 squared raised to the 7th power? Can anyone type in quickly to the chat and tell me that? Or get on the microphone and tell me that. Five to the 14th. When you have exponent raised to an exponent, you multiply those exponents together. Now in that 20, when I distribute the 6 to the 2 squared raised to the 6th power becomes 2 to the 12th, because again, you would multiply those exponents. 5 raised to the 6 is just 5 to the 6. And 2 to the 3rd raised to the negative 1 is 2 to the negative 3. Now I have my common elements. Now I have my common bases of 5, my common bases of 2, and I combine them as I see fit. The 2 to the negative 8th and the 2 to the positive 16, when you multiply across the same base, you add your exponents, that would become a 2 to the 8th. That 5 to the negative 8 and that 5 to the 14, you add those exponents, that would become a 5 to the 6th. Your 2 to the 12th and 2 to the negative 3 becomes a 2 to the 9th. And that 5 to the 6th is just now a 5 to the 6th. And now once I've broken it down into pieces, every next step feels much more manageable, including looking at these 5 to the 6s and saying, well, hi there, completely common term. I can just cancel you. And then 2 to the 8th over 2 to the 9th is either 1 over 2 or 2 to the negative 1, depending on how the answer choices have decided to express that, which is answer choice B. When we have a traditional exponent, you can go straight to the rules, and the rules are dependent on having a common element. You'll almost never have the common element presented immediately. You have to go out and find it. It will be hiding. And it's very, very likely that your common element is hiding in the bases. Break them down into primes and see what common things exist. Questions, comments, concerns from anybody? If you have no questions, no comments, or no concerns, just type in no comments, no questions. All right. Moving on to our non-traditional. I would actually like a moment for everyone to think about a realistic assessment of what you do for this problem. Think strategy, don't dive in. Realistically, what would you do? Alex, can you get on the microphone?
I cannot, and I was just sharing the page. I actually haven't started yet.
Oh, can you see the problem that's on the page?
Yes.
Realistically, how would you do this if you saw this on the test?
Personally, I would start with the clearing out those twos. It's pretty easy. I mean, you have 4, 4, 4 times 2, 8. Like you just quickly clear out the numerators. And then given the fact that you have a divided by, I personally prefer the notation where I can show it as times and I flip it where that is the numerator over 1 kind of thing.
Oh, interesting. So
And
you're
then
listening, you
also
would
with
say,
the, I like to write the exponent. So I write 5 to the half, 3 to the half. I like it with putting it as halves.
hmm,
And then I can look at it as, yeah, I like doing that.
8/16, so that's going to be 32 over those two parentheses. And then you do like 32 times 1 over this? Like 1 over those parentheses?
I like to look at it that way.
Okay. So the final question becomes, how would you resolve that raised to the half mess in the denominator?
Let's see. I love how I'm I have the hot seat. Okay.
And you can, so my rule is always, Chris, I want to just pass off to co-counsel. Normally in a class, you would call on one of your colleagues, but since this is not a traditional class, you just pass off to me. So if you want to be off the hot seat, just let me know.
No, really quickly. So I was just gonna say, one thing I was gonna ask is, how would it hypothetically work if I wanted to distribute? For example, if I want to do 5 to the half times 5 to the half, 5 to the half times -3 half. You see what I'm saying? The distributive property.
Yes. Yes.
That's where
When you
my
see
head went, and that's how I've liked it with the exponents.
when you see non-traditional exponents, you will usually have a common term or disguised quadratic issue. And that's what you actually have in that denominator. That's what you're noticing. That distribution is treating it like a quadratic because that's what it is.
Yay.
It's actually, this is a disguised a plus b, a minus b. Now this is open to the room, in the mic or in the chat. Do we have that quadratic memorized? Can you tell me the other form very quickly?
Me?
Anyone? If you're there, if you got it, Alex, go ahead.
I forgot it, but I do know what you're getting at.
So we want to memorize our 3 main quadratics. Let me just add a page in here. Our 3 most common quadratics. They are your a plus b quantity squared, your a minus b quantity squared, and your a plus b, a minus b. The a plus b squared, a plus b, a plus b. When you distribute that, you get your a squared. You get, so you distribute there, a squared plus ab. You distribute here. BA and AB are the same thing. You distribute here, you get a b squared. And so we will get a squared plus b squared plus 2ab. You may notice that I'm writing that in a different order than is commonly seen. I'll explain why in just a moment. It's not a math reason, it's a me reason. My a minus b squared, a minus b times a minus b, again, distribute, you'll get a squared minus ab, distribute, you'll get another minus ab, and you'll get a positive b squared. Watch that negative times negative, it stays positive. And now you get an a squared plus b squared minus 2ab. And then for your third one, a plus b, a minus b, you would get a squared. You would get minus ab, you'll get a plus ab, and you'll get a minus b squared, and those middle terms actually cancel. And you'll get a squared minus b squared. And this, now we see the reason why I like to write it with the squared terms first, because when I'm thinking this is like a flashcard or memorization idea, there's something visually appealing to me about having all the squared terms line up, so I can see which of them has the plus and the minus, and which of them has this little tacked on third term. And so I would look at this and we would say, well, that's just an a squared minus b squared in disguise. Now, that said, Alex, I want you to come back to me for a moment. Can you get back on the mic? There you go, perfect. You said your initial reaction to say, forget the exponents, the numbers are small enough that I can just run the numbers.
For the numerator, yes.
Well, why are you fighting that urge for the denominator? Your calculator on the test has a square root button.
Does it?
It is the only nice button that you have. It does not have higher order roots. It does not have any other exponents, but it has square root.
Because I thought it didn't. Oh,
That
okay.
is the only nice higher order function that your calculator has. So you can grab
By default,
5.
I always have the half power. I always have the square root. So then I could have just done
Uh-huh.
those two numbers together. Okay. And then I just multiply those two values. Got it.
And now just take a moment. If you take this calculator approach, know that you are making an approximation. So give yourself a lot of decimal backup. Many people only write one decimal place. No, no, no. Give yourself at least 3 because you got to make your approximation as good as it possibly can be. So I just grabbed square root of 5 in the calculator and I get 2.236. Square root of 3, I know it's 1.7 something, but let's find out what it is exactly. 1.732. And so I can take 2.236, add that to 1.732, and I'll get 3.968. And I'm really hoping this is going to work because this is not the way that I normally do the problem, but I want to show you that the calculator does exist. When I say hope that it works, I mean I hope that I don't mistype in the calculator here because that'd be embarrassing, and it can happen. And I'd have 0.504. And I would just say, let's just do that mess. 32, and then 3.968 times 0.504, 968, is 1.999872. I'm pretty sure that's a 2. And so 32 divided by 2 is 16, and that's math that I can do. If you see something that can be done in the calculator, no shame in that. The issue is we need to know a backup, because if this is 2 raised to the 12th plus 2 raised to the 12th plus 2 raised to the 13th plus 2 raised to the 14th, that's not math we're going to be able to do. And so we need to have a backup here, and I want to make sure I'm going to copy and paste this page so that we have a record of both approaches. Make sure that we can do the algebra. Question to the group. When you look at that numerator, and again, the idea that if we recognize non-traditional exponents, we are usually dealing with a common term or disguised quadratics or both. What common term exists in every individual component? The 2 squared, the 2 squared, the 2 to the 3rd, the 2 to the 4th, all of them have a common element. What is it? But the base number raised to what power, Joshua? 2 raised to what power? Margaret, was your answer to the second power? Is that what you're saying? Yes. Exponents and factorials. This is true for factorials as well. Exponents and factorials are like little nesting dolls. You pull off the big one, there's a smaller one inside. Pull off the next one, smaller one inside. Pull off the next one, smaller inside. So this 2 to the 3rd has a 2 to the 2nd right inside of it. This 2 to the 4th has a 2 to the 3rd and a 2 to the 2nd right inside of it. So basically, I can pull out that smallest little nesting doll and say, I can just take out that common term. 3 plus signs. 2 to the 2nd times 1 would maintain my original 2 to the 2nd. 2 to the 2nd times 1 would maintain my next 2 to the 2nd. 2 to the 2nd times 2 to the 1st would maintain the 2 to the 3rd. And 2 to the 2nd times 2 to the 2nd would maintain that 2 to the 4th. Now, we recognize that this denominator right here is an a squared minus b squared. Square root of 5 squared is just 5. square root of 3 squared is just 3. Now I have 4 times 2, 4, 4. 4 times 8 divided by 2, which will still be 16. When you see non-traditional exponents, exponents mixed with addition or subtraction ideas, ask whether you have common term or disguised quadratic game going on. You probably do. Questions, comments, concerns. If you're good, say no questions, no comments. If you do have questions, let me know. I'm glad you're finding it helpful, Margaret. What do we want to see next? Well, no, I'm going to show you and I'm going to ask. Could there be a problem that does a cubed root? You mean something like this?
I was thinking where it'd be kind of, it wouldn't really work for the quadratic rule, like where you'd have to fully flesh it out rather than be able to take the shortcut.
No, cubed roots, so quadratics are all about like exponents that are derived around even terms. So like a square root or a fourth root might be a very, very complicated quadratic, or something squared, something to the fourth, something to the eighth would be a quadratic. But if you have something raised to like an exponent that's based on odd terms, something raised to the ninth,
Yeah.
or something raised to the third root, those are usually not quadratics.
No, I'm saying you wouldn't be able to do a quadratic. You would have to just fully distribute out.
Yeah, and
Okay.
that'd be a mess. We've actually already touched on this idea, so I'm going to leave this one alone for a second. This problem. You might look at this and say, it's powers of 10. And it can be. But do we see exponents? Yes, we do. Do we see multiplication and division? Yes, we do. Do we see anything besides multiplication and divisions for any of these exponents? We do not. Could treat this as a traditional exponents problem as well. So there's a little bit of mix of powers of 10, a little bit of traditional exponents here. Everybody take a few moments and give it a try. Oh, quick thing. When you start to see decimals to this size, be aware that your calculator might crap out on you. The calculator can only hold about 6 to 7 digits. And so when you get to numbers that are larger than the millions, or when you get to numbers that have like 7 or 8 decimal places, if there's a possibility that that's going to be the end result of a problem, the calculator is not going to be helpful for you. So this one would be safest to have an algebra background to fall back on. Everybody take a few moments, give it a try. Margaret, Ashley, Joshua, how are you feeling? Give me something in the chat. Give me some kind of emoji. How are you feeling about it? Joshua, can you briefly describe your first step in the chat? And while Joshua is doing that, Margaret, do you feel you approach this through a powers of 10 idea or an exponent theory idea or sort of a mix? Or did you do something completely different? Ah, fair. Okay. Margaret, did you find that that happened here? All right. So what did you find intimidating? Was it the massive decimal or the power of 10 or both? I don't usually exponents with that small of a decimal. That large of a decimal. Okay. Are you familiar with what the powers of 10 do? All right. Well, that's one place where you can start. You could just build it in the calculator first and say, well, 0.1230 zeros and then a 25 and then 10 to the fourth. Powers of 10, when you see positive powers of 10 like this is just about how many zeros at the end of it. 10 to the first is 10, 10 to the second is 100, 10 to the third is 1000. It's always just about how many zeros are after it. By the same token, 10 to the 0 is just 1. Everything raised to the 0 power is 1, but 10 to the 0 is just a symbol to say that there are no zeros on the end of this 1. And then my negative powers of 10 are decimal place movements. So 10 to the negative 1 would be 1 decimal place on it. 10 to the negative 2, 2 decimal places on that. I say 2 while I'm writing. I start to write the number 2 when it should be the number 1. So you could look at this and say this is 0.00025 times 1, 2, 3, 4 zeros. And you could see if that can go in the calculator. Or once we get to some powers of 10 knowledge, I can say, all right, 4 powers of 10, that's going to be 4 decimal place movements. 1, 2, 3, 4. So n is the same thing as 2.5. Using that same concept for m, what will m be? Just the plain value after apply the power of 10. Yes, it will. 0.5. And now you've got options here. You can just chunk that into the calculator, or you can recognize that I can essentially move the decimals because what I'm doing is multiplying my fraction by something that is functionally 1. Multiply it by 10 over 10, and that becomes 25 over 5, which is 5. And yes, 5 is most definitively larger than 0.5. This is a pure powers of 10 approach. Anyone have questions, comments, concerns about this approach to the problem? Now we could also treat this as sort of a mixture of exponents theory. That 1, 2, 3, 4, 5 decimals in 0.00025 means that I can rewrite that as 25 times 10 to the minus 5, and then that is times 10 to the 4. All of this is just another way of writing that. Every decimal place movement is a negative power of 10. Why we multiplied 0.25 by 10? Are you speaking of right here?
Yeah, so in the numerator and the denominator, because if the 0.25 is the times 4,
Well,
uh,
first of all, it's 2.5.
okay.
But the idea behind this is just trying to get rid of the decimals in both. You can always multiply a fraction by something that is functionally 1.
Okay. So
10
you
over
didn't
10
have
is
to, it was
4.
just to get rid
No, this
of
is
I got you.
just a visual to get rid of the decimal. I mean,
Okay,
honestly, at
thank
this point, grab your calculator. But that's why. So that 0.00025, 25 times 10 to the minus 5. 5 decimal places, 5 negative powers of 10. 0.005 can be written as 5 times 10 to the minus 3. And that, in turn, would be times 10 to the 2. That and that are the same thing. And now, if I wish, I can restate this as 25 times 10 to the minus 1. And 5 times 10 to the minus 1. Again, this 10 to the minus 5 times 10 to the 4. And 10 to the minus 3 times 10 to the 2. Common bases in an exponents in a traditional exponents game, you combine those exponents by adding them. That becomes your 10 to the minus 1 right there. Now you got those completely common terms, cancel those off. 25 divided by 5 is 5 again, quantity A. Either way we shake it, quantity A is always larger here. Again, I'll hold here to see if anyone has questions, comments, or concerns. Grab another one. Let's grab the somewhat sneaky one. The image quality here is not perfect, but that is 5 to the k plus 1 equals 2000. And we want to know 5 to the k, and then after I have 5 to the k, plus 1 to that entire thing. Now, this problem is very sneaky because many times, many people are going to look at that 2000 and think, let's break that 2000 into prime factors. And I'll go, all right, so 2000, that is a 2 times 1000, and then eventually get it down to 1000 is 10 to the third, so 10, 10, 10, 25, 25, 25. However you shake it, that would be the prime breakdown of 2000. Now that is mathematically valid, but it's almost certainly not what you want to do here. And the reason is that is your approach to a traditional exponents problem. Traditional exponents problem, it is very likely breaking things down into prime bases is going to show you common elements and allow you to combine common terms and make the problem much simpler than it first appears. Why should I not expect a traditional exponents solution to this problem? There is addition. You have that, you have that. You should be thinking, I don't think this is traditional. I think I'm going to have to be a bit more creative. And the creativity comes in how we address this complicated exponent. Now that's a question I'm going to hold and give all of you a chance to consider. What is something we can do to deal with that needlessly complicated exponent? Alex, by all means.
I mean, my logic is immediately questioning, for example, some of these options of C, D, and E. For example, if 5 to the K plus 1, because so first off, are you trying to get the value of K? Correct?
They never asked for the value of K.
They're trying to get the value of 5 to the K plus 1. Wait, is it plus 1 or is it 5? I'm confused. This notation looks different on. Oh,
So it's 5 to the K is a thing. And then once you have that thing, you add 1 to it at the end.
now I'm getting it. Apologies. Okay.
It's all right. They don't care about the value for K. They never asked for that.
My first thing is I'd want to test it. They gave you a couple of options of how to test it by figuring out, like, if you were to say do 5 to the, oh, never mind. I give up. I got the wrong. Apologies.
It's okay. You were thinking test the answer choices?
I was going to do a test answer choice, but it doesn't work unless you first identify what K is to plug in for K to the next solution to get the 5 to the K plus 1.
Yep. Plugging in the answer choices works beautifully if your answer choices are a single discrete component of the problem. If my answer choices were just K, I could do it that way. But when my answer choices are some complex mixture of elements, plugging in the answer choices is actually sadly not an option. The GRE has a truly interesting love of what I call backwards math. Just put in an old slide here. GRE backwards math with exponents. Open question of the room. What is 2 to the second times 2 to the fourth? Leave it in exponent form, please. Two to the sixth. And you get there by adding your exponents. The GRE will give you these situations where you're meant to see something like a 2 to the 6 and recognize that, wait, that can be written as a 2 to the second, a 2 to the 2 plus 4. 2 plus 4, Chris, write the correct numbers. Which can be written as, there you are, Margaret, 2 to the 2 times 2 to the 4. It's actually what we saw in, where were you? This common term variation. Recognizing that this 2 to the 4 is a 2 to the 2 times 2 to the 2. Taking it and taking one item and breaking it into pieces. What we have here, this 5 to the K plus 1, that is one item which we can break into two separate pieces. 5 to the K times 5 to the 1, and 5 to the 1 is just 5. Do we see the next step? Or at this point, we might see the answer. Divide by 5. Divide both sides by 5 to begin isolating that 5 to the K component. And now, again, the natural interesting thing is to say, I can't solve for K. 400 is not a power of 5. There is no solving for k in this problem. They didn't want us to. All they wanted to do is say, find this thing and add 1 to it. How are we feeling? I'll tell you that the work through of this problem reminds me of a conversation I had with a colleague of mine, Dimitri. God, probably about a year and a half ago now. He and I were working together writing some of the Manhattan Prep explanations for new GMAT problems that have been published in the new version of the official guide. And one of us would write the explanation, the other would edit it. So I'd write one, he would edit my work, he would write one, I would edit his work, and we'd meet to discuss occasionally. And in one of our meetings, he looks at me and says, Chris, do you ever feel like an asshole writing these explanations sometimes? And I started laughing and I was like, not normally, Dimitri, no. He's like, well, I just feel like writing these explanations is like saying, hey, just do this clever thing and then the problem becomes really easy. Like I'm just telling him, just be clever. And that's not helpful. And this is really one of those borderline things where it's almost like trying to say, hey, just see this clever thing. Yay. And then it's easy. And I really want to push away from that. Yeah, especially when you're time crunch. I try hard to push away from the thing about how would I know? And for me, there are two things that would suggest it here. And this is what you look for when you study and you realize that, oh, wow, that was really clever. That was really interesting. Push back and say, how would I know? And there are two things. The first is to look at this and go, with the addition, this is not traditional exponents. There just be prepared for something a little bit more unusual, more creative. And then the next component is take the complicated, take the strange element and see if you can break it into pieces. And that's what's happening here. This is the weird part of this problem. Can I break that down somehow? Now, seeing that it has to go 5 to the k times 5 to the 1, I mean, honestly, that's just a leap. But at least with those two elements, it's not traditional, and there's a weird complication here that I've got to address, so I at least know where to focus my attention. That's what I can feel when I can look and say, okay, I at least have a feeling that I could see something similar in the future. All right. We just have a few minutes left tonight. I want to say just a few things here. First of all, did all of you receive an email from me? I think it was actually just yesterday, maybe Saturday. Did you all get an email from me? Alex did. Ashley did. Margaret, Joshua, did you? So Joshua, you don't have it. Hang on one second. So that's my email. If you would like to get a copy of the slide deck that I prepared for this evening, shoot me an email. I'll be happy to email you a PDF of it. So just let me know if you want that. I want to say that first here. And then looking at the last problem for this night. This problem. Traditional exponents. I see exponents, I see roots, only multiplication and division happening here. This one would be an opportunity for smart numbers. Pick a number for x that's something nice to go underneath the square root. The trouble here is that you probably have to pick something nice for x that's good to go under a square root and a cube root. So you'd have to quickly see that 64 would work. 64 would be is 8 squared, but it's also 4 cubed. And realistically, that's only like the first number that comes to mind that would be nice for that. So you'd have to quickly gravitate towards that to do a number testing thing. This is one where my urge would be number testing, but I'd have a hard time figuring out which number. The reason I wanted to close with this problem is because there is an algebraic, I guess, mantra, for lack of a better term, that I want all of you to consider during your studies and during your preparation, and that is no mixed formats. I see exponents and I see roots. No. I'm going to pick one, and I'm going to make everything that format. And because I agree with Alex most of the time and what she said about, exponents versus roots, let's pick exponents, I'm not going to touch the x to the 3 halves. I'm going to leave that alone. And I'm going to take my answer choices and say, all right, answer choices, every single one of you that has a root on you, you are becoming an exponent. And every root is just a fractional exponents. And my friends, what do we do with exponents when we multiply across the same base? Additional exponents, we can go straight to rules. What is my rule?
Adding.
I will add them. So I'll take 2 plus 1/2, which is the same thing as 4 halves plus 1/2. And I'll say 5 halves. So this becomes x to the 5 halves. Not what I wanted. X to the first times x to the 1/2. 1 plus 1/2 becomes 2 halves plus 1/2, which will become 3 halves. And this will be, well, hi there, x to the 3 halves. Yes, you are exactly what I wanted. And I would select choice B. Now, just to finish this off, that x squared raised to the cube root is x squared. Every root is just a fractional exponent. So that would be x squared raised to the 1/3 power. Exponent raised to exponent, you multiply them. So that is x to the 2/3 power. Again, not what I wanted. X to the first cube root, so raised to the 1/3 power, will be x to the 1/3. Again, not what I wanted. And this x to the third raised to the second, multiply those two, x to the 6th, still though, not what I wanted. No mixed formats. If I see fractions versus decimals, no, I'm picking one. Usually fractions. Fractions versus percents, no, I'm picking one. We saw here decimals versus powers of 10, no, I'm picking one. Try as much as possible to pick one format only. So we have here 3 large pages of notes. Traditional versus non-traditional was the main theme I wanted to address tonight. That did, however, lead to a discussion of the fact that I want to have some of these common quadratics memorized, and just recognize that the GRE will like to give you backwards math. They take a unified element, and your job is to break it into pieces. I'm glad you found it helpful, Margaret. That is our time for the evening, everyone. I will hold around here for a few more minutes in case anybody has questions before we close, though. Thank you all for being very active. Thank you all for being either on the microphone or in the chat. Ashley, I wish you the best of luck on Friday. And wherever you're at the ballpark, I hope it's a good game. But if you have no questions, feel free to sign off. If you do have a question, just pop it in.
I have a question.
Dude, Alex, go ahead.
I assume that you offer like regular tutoring outside, like do you have with the program with the Manhattan Prep? How does this work if we want additional time with you?
Yes, I do tutoring through Manhattan Prep. It has to be through Manhattan Prep because I use their resources.
Understood.
So, absolutely. If you'd be interested in that, just feel free to reach out.
Okay.
That's actually right now, that's actually the bulk of what I do.
Okay, I'm gonna do that. So I'll send it to that email that you gave then. Okay.
Absolutely. Just a quick note, Alex. As much as I would like to, I cannot promise a reply before Thursday. My day tomorrow is literally 9 a.m. to 10 p.m. almost straight through. It was one of those, like I mentioned a moment ago, that tutoring is most of what I'm doing right now. It's a weird thing where all of my students had availability on Wednesday this week and almost nothing else. So I've got a packed day
Totally
tomorrow.
fair. I have an unrealistic date. I'm supposed to take my GRE on Monday, and I just really feel like
Yeah.
some gap that I could use, some tension with. So thank you. We'll connect
course.
probably Thursday then.
All right, sounds good.
All right, talk later. Bye.
Talk later.